Hello students, in this class we are going to discuss about nice and ugly domains, and again one topic called domain testing. So now let's get into our topic. So now let us see what is a domain testing. What is a nice and ugly domains. So when coming to a topic called nice domains, now let us see where these concepts domain come from. The domains are will be defined by an imperfect iterative process. Suppose we are going to perform testing on some iterations, means so many times we have to perform. So when you are performing when you are performing imperfect, whether it is not a perfect thing, it is an imperfect iterative process aimed at achieving whether user by for the user, buyer or voter satisfaction. Suppose what is the user satisfaction? The user has to provide the best product, the buyer has to receive the best product, the voter, what is the voter satisfaction? Here the voter satisfaction is he has to use the best product. So based upon all these satisfactions, we have to achieve their goal of such that we have to perform the perfect iterative process. So for that, the implemented domains that can't be completed are inconsistent. Every input will be processed possibly forever. For example, the inconsistent domains will be made should whatever the inconsistent domains that should be made consistent, and the conversely specified domains can be incomplete or inconsistent. So incompleted in the context means that there are input vectors for which no path is specified, and here the inconsistent means there are at least two contradictory specifications over the same segment of the input space. So here whenever you are going to use the conversely specified domains where it is incomplete or inconsistent, so in this context means there are the input vectors with no path is specified, and the inconsistent means there are at least two contradictory specifications over the same segment of the input space. See, if you have observed this, these are the some of the properties of the nice domains. When we can say it is a nice domain, so it should be a linear, and it should be complete, and it should be systematic, and it should be orthogonal, consistently closed, convex, and simply connected. So these are the properties that should maintain by a domain, whether it should be a nice domain, when it should be say as a nice domain. What are the properties? Linear, complete, systematic, and orthogonal, consistently closed, convex, and simply connected. So to the extent the domains have these properties of the domain testing, and it is easy as the testing gets. See, suppose if it is a if we are having dimensions in this domains also, here the bug frequency is lesser than the lesser for the domain than for the ugly domain. See, if you have observed, this is a row and this is a two-dimensional domain, and if you have divided this one into the different domains, here we have to test, and we have to perform, we don't know how many iterations that we need, and we have to perform different so many iterations on that. So this is one domain, 1 2 3 just what are the domains based upon the code that we have written, we have to write the domains for that. So this is the two-dimensional domain, this is the example for the two-dimensional domain. Okay, see, then what are the linear and non-linear boundaries? See, these are the some of the properties. When it should be a nice domain, it contains some properties. No, this is one of the property. It should be a linear. Then now let us see what is a linear and non-linear boundaries. See, nice domain boundaries are defined by linear inequalities or equations. So the impact on testing stems from the fact that it takes only 2 points to determine the straight line and 3 points to determine a plane, and in general n plus 1 point to determine the n-dimensional hyperplane. See, without any equalities or without any equations, so we have already discussed in the previous class that we are coming for the we are going to the mathematical concept. Why? Because in order to solve all these expressions, we have to, the machine doesn't understand this particular type of language. So in order to solve that particular issue, we have to learn this type of mathematical expressions. For that also, we have to check whether the domain properties are satisfying or not, whether it is satisfying any linear inequalities or equations or not. You have to check, and the impact on testing stems from the fact that it takes only 2 points to determine the straight line. whether we have to check whether it is a straight line or 3 points to determine a plane. We have already these mathematics concepts. We have the closure concept. We have to play in calculus. We are having this plane, this hyperplane, one dimensional hyperplane, and dimensional. Why we are going for that planes means to solve that particular problem we have to draw it into planes or boundaries. Just like that we have to solve that particular module. So we have to determine the plane in general, that n+1 point to determine the n dimensional hyperplane. So in practice, more than 99.99% of all boundary predicates are either linear or can be linearized by the simple variable transformations. It is not a single variable transformation, it is a multiple variable transformation. So if you have observed this about the complete boundaries, what is a complete boundary? A nice domain boundary are complete in that they span the number space from plus to minus infinity in all the dimensions. So this figure 4.4 shows that the incomplete boundaries A and E have the gaps. Such boundaries can come out because the path that hypothetically correspond to them is unachievable, because the inputs that are constrained in such a way that such values can't exist because of the compound predicates. So that definitely will define a single boundary, or because of the redundant predicates we have to convert such boundary values to a null set. So the advantage of the complete boundaries is that one set of tests is needed to confirm the boundary no matter how many domains it bounds. So if the boundary is chopped up and has holes in it, then every segment of that boundary must be tested for a domain it bounds. So if it is the complete boundary, the nice domain boundaries are the complete in that they span the number space from plus to minus. That means from larger values to least values, it can be written in all the dimensions. That is in x dimension, y dimension, that is one dimensional or two dimensional or three dimensional. Okay. Then such boundaries can come about because the path that hypothetically it will corresponds to them is unachievable, because the inputs are constrained in such a way that such values can't exist because of the compound predicate. So if you have observed this one, this is an incomplete domain boundary. See, this is A to A, this is domain A, and if you have observed that this is not a complete domain boundary, this is B, this is each and every domain has a relationship between them, but this is not a complete domain boundary, this is a incomplete domain boundary. See, if it is a systematic boundaries, systematic boundary means that the boundary inequalities related by a simple function such as a constant. Suppose if you have observed this example, the domain boundaries for u and v differ only by a constant. See, we are having the domains two domains. If you have taken this example, suppose we are assuming that we are having the two domains, that is one is u and another one is v. So these two are differ only by a constant. See, this one is f1 of x is greater, this is some constant k, and this one is this is one function, this is one function representing u, and this is another function representing v. Just like that, these are the three cases, that is greater than or equal to, greater than or this is two functions. This is if you have observed f1 of x greater than or equal to k1, this is one constant, this is another constant. Okay, suppose from this we can say that fi of up to n boundaries, we can say that f1 up to f5 we are going to perform the iterations on the domains. Okay, where fi is the arbitrary linear function and x is the input vector and k and c are the constants. G of I comma c is a descendant function. This is another function that the result that we are going to get over I and c that yields the constant such as, suppose, k plus I comma c. So for the first example is a set of parallel lines and the second example is a set of systematically spaced parallel lines. such as spokes of a wheel, if equally spaced in angles, systematic. If the boundaries are systematic and if you have tied down a generate test for it, then the test for the test boundaries can be set automatically generated. So this is how we are going to set the systematic boundaries. Understand? If you are having some inequalities in the boundaries, we have to perform the simple function. We have to apply the function constant. Suppose if we are having two domains, we have to take the two functions. For that function we have to keep the constant k, such that from that we can generate another, such that we can generate the such as k plus ic. Just like that we can generate the another constant. And another example is a set of systematically spaced parallel lines. So suppose if the boundaries are systematic, then it will be tied down to generate the test for it. So if the test of the rest boundaries in set can be automatically generated. See, then what are the orthogonal boundaries? Two boundary sets U and V are said to be orthogonal if every inequality in V is perpendicular to inequality in U. See, both the domains U and V having some inequalities. So these inequalities are not parallel. If the inequalities are perpendicular to each other in the boundaries U and V, then we can say it as a orthogonal boundaries. So if two boundary sets are orthogonal, then they can be tested independently. It cannot be tested dependently, it can be tested independently. So if you have observed if you have observed the figure in the next slide, uh, the boundaries, we have 6 boundaries u and 4 in V. We can confirm the boundary properties, and the number of tests proportional to is 6 plus 4, that is 10. This is O of n is the time complexity that we are going to take. That is if you have the tilt boundaries to get the figure. So we must now test the insertions, and we have gone from a linear number of cases to the quadratic, that is from the time complexity may increase from O of n to O of n square. See, these are the, see, if you have observed these two boundaries, uh, here we have said that if it is orthogonal, if you are both the inequalities in the two boundaries are perpendicular. See, here if you observe this figure, here if you assume this one as inequalities, here we are having this is one boundary and this is another boundary. So the inequalities in one boundary is perpendicular to the inequality in the other. Okay. See, this one is also, if you have observed this one is one boundary, this is one boundary and this is another boundary. So this is non-orthogonal boundaries. Okay. Why? Because this is not a this is one boundary is not perpendicular to the another boundary. So this is a difference between the orthogonal domain boundary and non-orthogonal domain boundary. See, then what is a closure consistency? So this the in the next slide we are having some figure. It shows that the another desirable domain property and the boundary closures are the consistent and systematic. So the shaded areas on the boundary denote that the boundary belongs to the domain in which the shading lies. The boundary lines belongs to domains on the right. So the consistent closure means that there is a simple pattern to the closures. For example, if we are using same relational operator for all the boundaries, it is a set of parallel boundary. Okay, so we can say it as a closure consistency, such that the simple pattern we have, the what are the simple pattern that we are taking there to the closures. For example, if you have taken some relational operator for all the boundaries, we are having some set of parallel boundaries. Okay, so now let us see about the convex. Convex is a geometric figure if any number of decisions is convex, if you can take two arbitrary points on any two different boundaries, join them by a line, and all the points on that line lie within a figure. So the nice domains are convex, dirty domains are not convex. Okay. So whenever we can see is a nice domain, we can simply say it is a convex. Okay. So you can smell a suspected convexity. Convexity means about the that is a term related to the convex. You can relate that about the convexity such that you can see the phases just like that we can expect. However, but not, this is not like that. But whenever in a programming, it's often but it's in the specification that kill you. So then why it is simply connected? See, nice domains nice domains are always simply connected. That is, they are in the one piece rather than pieces all over the place intersected with other domains. So, simple connectivity is a weaker requirement than convexity. If a domain is a convex, it is simply connected, but not vice versa. So, if you have considered the domain boundary defined by a compound predicate of the Boolean, so from ABC, such that the input space is divided into two domains. One is defined by ABC and therefore the other is defined by its negation. And for example, suppose if we have defined the valid numbers and those lying between the 10 and 17 inclusive, the valid numbers are disconnected domain consisting of the numbers less than 10 and greater than 17. So the simple connectivity, especially for default cases, may be impossible. That is not a possible thing, it may be a impossible. So next one is ugly domain. Some domains are born ugly and some are uglified by a bad specifications. Every specification of the ugly domain by the programmer is either good or bad. Sometimes it may be a good thing or sometimes it may be a bad. So the programmers in search of nice solutions will simplify the essential complexity without of existence. The testers in search brilliant insights will be blind to essential complexity and therefore miss important cases. Suppose if the ugliness results from the bad specifications and the programmer specification is harmless, then the programmer is made ugly to be good. So, but if the domain's complexity is essential, such the simplifications the constitute bugs. So, non-linear boundaries are so rare in the ordinary programming that there is no information on how the programmers might correct the such boundaries if they are essential. See if it whether you have to see that whether if it is essential thing or non-essential thing, you have to see whether in nonlinear boundaries are so rare in the ordinary programming that they are having no information on how the programmers might correct such boundaries if they are essential. Okay. See how the ambiguity and contradiction may arise. Here, the domain ambiguities are the holes in the input space, and here the holes may lie within the domains or in the cracks between the domains. So the two types of contextions are only two types of contextions are possible: overlap domain specifications and overlap closure specification. So here, if you have observed this figure, it shows the domain. See here, this is one domain and this is another domain, and this part is overlapped between the two domains. So this is having we are having the chance to get the ambiguity. Okay, why you are having so? See, if it is a concept called uh, if we are having the holes in the input space and the holes may lie within the domains or the cracks between the domains, then we are having the two types of contextions. One is those contextions that is possible. One is overlapped domain specifications and second one is overlapped closure specifications. This one shows the overlapped domains that shows the dual closure assignment. Okay, this is contection dual closure. This is ambiguity. Okay, here we may get the contection. Here we may get the sorry. Here we may get the ambiguity. So, from this is the overlapped domain. Okay. Then how we are going to simplify this particular kind of topology? The programmers and testers reaction to the complex domains is the same. If we are going to simplify it, there are three generic cases. First one is concavities, second one is holes, and third one is disconnected pieces. See, if the programmers introduce the bugs and testers misdesign that cases by smoothing out the concavities and filling the holes and joining the disconnected pieces. See, if it is like this, simply at this place and this place, if you are going to fill some holes, then simply we will make it. We can make this particular uneven even surface, that is we are making it into the convex. Okay, suppose in this case we are having some holes, so instead of keeping that holes like that, here you are going to fill in that holes. Okay, see, here also from this we can simplify this particular kind of topology. This is the way that how this is the way we are going to get the topology like this. Okay, next one. See, if these are the boundary classes, the domain boundaries are parallel but have the closures that go every with which way, left, right, just like that. The natural reaction is to make the closures go the same way. See, this is consistent direction. First one is the consistent direction, and next one is the force in the closure consistency. See, if you have observed this one, this is having some consistent rule. This is to be forced to be like that. Suppose if the domain boundaries are parallel like this, we are having the closure property that go every with the natural reaction to make the closures go to the same way. See, we are coming to this concept called domain testing strategy. Domain testing strategy is the simple, although possibly it is slow. How we are going to test this domain strategy? It is defined by boundaries. Therefore, the domain testing concentrates on the points near the boundaries. So we have to classify when we have to go wrong with the boundaries. Then we can define the test strategy for each case. Then we can pick enough points to test all recognized kinds of boundary errors. Because every boundary serves at least two different domains, the test points used to check one domain and can also be used to check the adjacent domains. So we can, from this we can remove the redundant test points. So run the tests and by the possessed analysis and determine if any boundaries are faulty and if have how. So from this we can run the enough tests to verify the every boundary for every domain. From this we can run the test to verify the every boundary for the every domain. So observe this one about the domain bugs and how to test them. If it is an interior point, and the interior means this is the interior point. Okay, this is the interior point. So if it is an interior point in the domain such that all the points within the arbitrary small distance are also in the domain. So a boundary point is one such that within the ellipse and neighborhood that are points both either in the domain or not in the domain. So an extreme point is a point that does not lie between any two other arbitrary but distinct points of a convex domain. See, this is the interior point and this is the boundary point which lies on the boundary. So it is a boundary point. It is in between the two boundaries. So we can say this one as the extreme point. Okay. So, and one point is a point on the boundary. If the domain boundary is closed, an off point is a point nearby the boundary but in the adjacent domain. So, if the boundary is open, an off point is a point nearby the boundary but in the domain is being tested. Observe this figure. You can remember this by the acronym. See, closed off outside. See, closed off outside, open off inside. So C O O I, So we can define it as a acronym. See here, this is a actually interior point. Here it is here if we are having one point, this exterior point, it lies on the boundary, so it is a boundary point. Here if we are having three other points called off points, so it shows the generic domain bugs, closures, and shifted boundaries, title boundaries, and the missing boundary. Okay, these are the shifted boundaries. These are the titled boundaries. This is a open or closed error. This is extra boundary, and this one is missing boundary. Okay.